our second module, we're going to be learning more about linear systems, but this time we're going to focus on application problems. Anytime I solve a word problem, I always read it at least 2 times, sometimes more. And the first time you read the problem, you want to read it very quickly and just focus on that last sentence. My first example says, a mail order garden equipment business shipped 120 packages one day. Customers were charged $3.50 for each standard delivery package and $7.50 for each express delivery package. Total shipping charges for the day were $5.96. Here's the sentence I'm going to focus on. How many of each kind of package were shipped? So I start by thinking about, well, what are the unknowns? What are they asking me to find? And there's 2 things they want me to find: the number of standard delivery and the number of express delivery packages. I'll assign variables. Let's make standard X, express delivery Y. Now I read the problem a second time, this time focusing on details. The first sentence tells me that the total number of packages was 120. That means if I add together both kinds of packages, it has to equal 120. So X plus Y is 120. The second sentence has to do with money. It costs $3.50 for each standard, $7.50 for each express delivery. So $3.50 times X times the number of packages, plus $7.50 times Y, the number of express packages, has to add up to the total amount of money, the $5.96. And there's my system. We can use substitution or elimination to solve this. I'll use elimination. I'm going to multiply that first equation by negative 3.5 so that the x's are eliminated. That gives me negative 3.5x minus 3.5y, and minus 3.5 times 120 is negative 420. If I add the equations together, the x's go away. I'm left with 4y equals 176. 176 divided by 4 is 44, so y equals 44. I'm going to take this number, plug it into that first equation. X plus 44 is 120. Subtract the 44, so x is 76. So that means we must have 76 standard delivery and 44 express delivery packages. Example 2. Erica has $60,000 to invest. She's putting part of the money at 5.5% interest and part at 6.5 interest. She wants the income from the interest, so the interest, to total $3,750 yearly. How much should she invest at each rate? So once again, I focus on that last sentence. How much should she invest at each rate? That means my unknowns, again, there's 2 of them, the amount at 5.5 and the amount at 6.5 interest. Now I read the problem again, focusing on the numbers, on the details. If she has $60,000 total to invest, that means if I add up the 2 accounts, X plus Y, it has to equal $60,000. Now her interest totals $3,750. We're going to always assume simple interest in this class, and so the interest she earns in the first account is just that percentage, 5.5% times X. Now when we do math with percent, we have to change it into a decimal. We have to move the decimal to the left 2 places. And so my second equation I have written in green. Basically, if I add up the interests, 0.055x plus 0.065y, it has to total 3,750. I'm going to use the elimination method again. If I want the x's to be eliminated, I've got to multiply that top equation by negative 0.055. So negative 0.055x, negative 0.055y, and negative 0.055 times 60,000 is negative 3,300. Add the equations together, the x's are eliminated, and you're left with 0.01y equals 450. If we divide by 0.01, that gives us y is 45,000. To solve for x, I'm going to plug the 45,000 into the first equation. If we subtract the 45,000, we get x equals 15,000. So $15,000 was invested at 5.5%, 45,000 at 6.5%. In this problem, let's see, in 1 hour, Anne can row 2 miles against the current, or 10 miles with the current. Find the speed of the current and Anne's speed in still water. So once again, I start by focusing on the unknowns. It's in that last sentence. I want to find the speed of the current and Anne's speed. That's going to be my x and my y. Now this problem is talking about motion, and so there's an important relationship we're going to use in our motion problems. We're going to use the fact that distance is always your speed, or your rate, times time. Now I like to organize this information in a table, keeping track of important distances, rates, and times. There's two situations we have to consider. She paddles against the current and with the current. So I'm going to start by filling in everything that I know. 2 miles, that's a distance against. 10 miles, distance with. The time that this is happening in is 1 hour, in 1 hour. The things that I don't know are the rates. When Anne is going against the current, the water is moving in the opposite direction as her. It's slowing her down. The net result is her speed will be whatever she paddles minus the water. Minus because the water is slowing her down. When she travels with the current, the water is moving in the same direction, and so the water is actually speeding her up. The net result is her speed is whatever she can paddle, that's the x, plus the water, plus y. Now to get my equations, I'm going to use the fact that distance equals rate times time. Each of these rows is going to turn into an equation. The distance 2 equals the rate, x minus y, times 1. And the same with the current case. I can distribute the 1. I have x minus y equals 2, x plus y equals 10. These equations are set up perfectly for elimination. Add them together, the y's disappear. 2x equals 12, divide by 2, x is 6. I'm going to take that 6, plug it into either equation. I'll plug it into the bottom one. So 6 plus y equals 10, subtract the 6, y equals 4. So that tells me Anne is rowing at a rate of 6 miles per hour, and the current is moving at a rate of 4 miles per hour. Finally, my last example is a mixture problem. How many liters of a 25% alcohol solution must be mixed with a 12% solution to get 13 liters of a 15% solution? So I have one solution that's too strong, one is too weak. I'm going to combine them to get something kind of in the middle. I'm dealing with percentages here, and so I'm going to remember the fact that the part is always equal to the percent times the whole, or percent times the total. That's my basic percent equation. Once again, I'm going to collect the numbers, the information into a table to help me stay organized. In this case, we are adding together a 25%, a 12% solution to equal some kind of mixture. I'm going to put those percentages in right away, writing them as decimals. The things that I'm solving for here are the total amount of the 25% solution, the total amount of the 12% solution. I know I need that mixture to total 13 liters. To fill in my part column, I use that relationship. Percent times total equals the part or the fraction of the solution that is alcohol. To get my equations, I'm going to use the fact that if we add together those first two rows, we add together the 25 and 12% solution, it has to equal the mixture. I write an equation describing that the totals have to add up, and also the part that is alcohol, has to add up. The 1.95 is 0.15 times 13. I'm going to solve this with elimination. I multiply the first equation by negative 0.25. I add the equations together. I get negative 0.13y equals negative 1.3. Divide by negative 0.13, and so y equals 10. I'll plug that 10 into the first equation. X plus 10 equals 13. Subtract the 10, so x is 3. That means we need 3 liters of the 25% solution and 10 liters of the 12% solution. So those are my 4 examples for applications of linear systems. There's lots of variations of these types of problems, but my advice is to focus on patterns, looking at the tables and noticing that there's certain patterns that are going to arise. As always, I'm happy to answer any questions you have on homework. Just send me an email or stop by during office hours.